Hi, welcome to the Apollo Launch Vehicle Digital Computer video. Yes, this is the LVDC board from an Apollo Saturn V rocket that took humans to the moon, of course, back in the 1960s. This was designed in the 60s, and this comes by courtesy of fellow video blogger Fran Blanche, and she's done some awesome reverse engineering stuff on this, and I'll link to her videos down below, and she passed this on to me to do something with. And well, what am I going to do with it that she hasn't already done? Well, I've got myself a precision source measure unit, so I thought that I'd measure some of these semiconductors inside here and see if they're still working after all these years. This was designed and built in the 1960s, so are the semiconductors still viable in these things? Do they still perform as diodes and transistors? Well, let's find out. Now, all of this Apollo hardware, of course, was state-of-the-art, designed to get humans to the moon, a very difficult task. And designing the early computers like this was groundbreaking stuff that really helped future computer technology, manufacturing technology, electronics, ICs, all sorts of things that we take for granted these days. A lot of it came from this sort of Apollo era hardware. So really fantastic legacy stuff we've got here. I love it. And as the name says, the Launch Vehicle Digital Computer is basically exactly as it says. This is the computer, or part of. It's one of the many boards that comprised the computer that controlled the Saturn V rocket as it launched, i.e. the guidance and everything else as it flew up and then was ultimately discarded. And there's a few of these littering the bottom of the ocean, of course, because, well, the rockets just fell into the ocean. I don't think they ever recovered them, or they might have recovered some bits from them or something like that. But this one never flew, obviously, otherwise it would we wouldn't have it in this sort of condition. And yeah, it's not in great condition because Fran's already done some work on it. She's depotted some of these chips, and here's a photo of actually depotting these things. It wasn't pretty. They had a pink sort of, epoxy type putty inside with a ceramic top, and these chips actually slide out from these little clips based on this board, and it's a very complex manufactured board for its era. I mean, obviously absolutely state-of-the-art for its time, and this is not a chip as you know them today. This is basically just got diodes and transistors in them. It's DTL, diode transistor logic, and that's pretty much it. But we do actually have a data sheet for a couple of these chips, so we do actually know the pinouts so we can test them. Now you can hopefully see some of those clips there that held in these chips, and I'll basically just slide in like that. Look at those vias. I mean, that's not unlike what you'd see these days, but the construction technology of this board is very significantly different to what you'd see these days on a board, but on a physical, typical printed circuit board these days. But anyway, look at those clips. Yeah, there's a lot of corrosion and gunk and all sorts of stuff on these things, but hopefully we can probe some of these things and or slide out a couple of these chips, because we've only got data sheet on a couple of these parts, but we do know the pinouts, so we can slide them out and hopefully still be able to probe the metallized pads on the side of these things. So right down in there, we've got to slide them out intact. I don't know how easy that's going to be. Fran has actually done it, so yeah, well, I've got to give it a go, and I've only got a couple of shots at it, so, well, fingers crossed. And whether or not we can still make contact to the metallized pads actually on that substrate material. Now, I have actually had a bit of success probing the back here, and even before I got the data sheet from Fran, I was able to actually probe out a couple of what appeared to be PN semiconductor junctions, i.e. diodes, inside this thing just by random probing. And you'll notice that there's no traces on the bottom at all. These are it's all internal layer stuff. So incredibly complex construction. This is a very multi-layer board. And as I said, you know, pretty different construction techniques, but not too dissimilar to the overall structure of what you get in a PCB these days. But yet, nothing on the bottom whatsoever. It's got this sort of covering on it. I don't even know what that covering is, but we can actually chip that away. It's all been chipped away from this area down here. So we'll just see if we can get just a closer up version of this board. I'll switch on my Tagano microscope here and let's go to the videotape. Alright, here we go. It looks fantastic under the microscope here, and here is the top view internal diagram of what's inside this inverter module here, INV. We only have the data sheet for two of them, the inverter and this what's called the AA chip here. So I've only got one inverter on this whole board, so fingers crossed, and two AA chips like this. And of course we can't measure them in circuit because we'll get errors due to however it's wired inside, you know. So really we have to try and get the chips, slide them out of these connectors on here to try and access the pins on these things. And basically that's the internal circuit diagram. We've got one transistor, two back-to-back diodes here, and some resistors. That's pretty much all that's inside this inverter module here, and this is why they call it diode transistor logic, DTL, because it uses diodes and transistors and pull-up resistors, and it forms your gates and your logic that way. So there you go, that's inside that one. And the AA module is even simpler than that. It doesn't even have any transistors. Here we go, these AA modules here, just a couple of anode common back-to-back diodes like that going out to separate pins there with a 2.5k pull-up resistor. And what we can do is zoom in here and take a look at a couple of these chips that Fran's already depotted for us. Look at that. Oh, I love this Tagano microscope. Very nice. And this one still has the chip in it. Look at that. You can see the chip there. And these two pins physically connected. That one's going off there. So that looks like a 3-pin device. These have, she's obviously accidentally or purposely ripped out the chips from these two here. And you can see some of that pot-in compound still in the corner down in there. Look at that. Oh, that's terrific. Can I zoom in any closer than that? That's the maximum zoom I can get on this Tagano microscope. But yeah, look at that. So it was potted with that, whatever material that is, I don't want to know. But you can see the metallized traces laid down in there. Very, very interesting. And if we angle that, we can really see those clips there. Check it out, and it is horribly corroded and rusted. But hopefully we can slide out these chips and then probe what's left of the metal. You can see parts of the metallized contacts still on there going inside the chip, and then there's got this wall around it with a ceramic top on it, and then they fill them with that potting compound, and these clips are somehow welded onto these metallized pads down on the board. Interesting construction technique. And check that out. We can see down some of the vias in there. Look at that. See the wall of those, and as I said, manufactured in the 1960s. State-of-the-art technology. Awesome. Shame it's not in better shape, but anyway, what do you expect? And there's some of the vias on the bottom side, and look at this bottom stuff looks quite fiberglassy, so yeah, it's something like that. It does peel off relatively okay. I have chipped away a little bit of this, and it does seem to come off. It's a bit easier towards the outside parts of the board, but as you get in, it gets a bit more difficult. So it certainly is very interesting technology. I love this stuff, and no date code on this particular model. I can't remember if Fran's actually was able to get a date on this one or not, but that, folks, is 1960s Apollo technology. Ah, you gotta love it. Now, it actually doesn't seem hugely difficult to clean up some of these pads here. I'm just using some isopropanol alcohol here, and that's cleaning up. Not bad. at all. Check that out. I rather like it. There you go, look at that, like I bought one. Now, I do know that this was state-of-the-art at the time, of course, but I can't help but think, why didn't they integrate this further? I mean, these chips that have got basically bugger all in them, an entire chip taking up this, and, well, presumably, I don't know what some of the other chips in here do, but say the inverter, for example, I mean, you know, we've just got like a couple of diodes and a transistor in there. Why didn't they, you know, this little piece of silicon down here, well, why didn't they just make it a bit larger? I know the silicon manufacturing technology back then was in its absolute infancy, but and this was, you know, pushing the state-of-the-art technology, but I just can't help but think why they just didn't pack more functionality into one device like that. I mean, it's not like they had this, you know, gigantic die in there to do a transistor and a couple of diodes. I mean, look, you know, that die in there is just one device. Why couldn't they just pack more of them in there and utilize all the pins? I mean, you know, we've got unused pins all over the place. I know it's like designed to be modular and things like that, and they have, you know, specific chips for specific purposes, but why they just couldn't do more? And I don't know, it just seems a bit limited to me, but you know, I mean, the constraints of the time, they probably designed this much earlier, and then as technology improved, they couldn't just, you know, wham, let's just change it all, you know, 5 years into the Apollo program or something like that. So really, they were probably stuck with what they had, and it was good enough. It did the job. And what we've got here is an Agilent B29128 Precision Source Measure Unit, or SMU, or SMU as they're known, and we can use one of these to test the semiconductors and actually characterize their voltage and current performance, i.e. get those characteristic curves that you see in the data sheets. I've done a teardown video on this if you want to see it. It's a really interesting beast inside, very expensive thing, and unfortunately I've only got it for another day or two, so I've got to send it back. But hopefully we can probe some semiconductors here, see if they're still usable. Let's go. Now, I won't bore you with the details of how exactly SMUs work and how to set them up, but we'll start out with just measuring a basic modern 1N4148 diode here, and this is what we get. So then we'll have a baseline of instruments set up to work against to characterize the diode performance inside these Apollo era chips. So here we go. If we probe it and we press measure, boom, there we go. We've taken 100 sample points and we get our characteristic diode curve. There it is, starting to ramp up at about 0.6 volts here, going all the way up. So that's what we'd expect of a typical diode from the Apollo era as well. I mean, you know, the voltages and currents and everything else might change a little bit, but we basically expect that PN junction characteristic curve shape. And what I'll do is I'll use these really fine pointed springy probes here so they can get decent pressure down on just the individual pins down in there. So I'll be able to probe, hopefully, and get through any oxidized coating on those pins or anything like that. So I'll start out just by trying to measure one in circuit on that inverter chip. Well, looky what we have here. It's a similar sort of characteristic curve, but not nearly sort of the voltages we expect. I've got 0 to 5 volts on the x-axis here, but it does actually curve up like a PN junction. I measured this one in circuit, of course, just one of the diodes inside the inverter chip, and you know, it's from 0 to 50 milliamps is the test currents I put in, and well, we're getting huge, you know, that's a large voltage drop across these diodes. I'm not sure what we would expect for the era, but they, you know, they've got to be like a, you know, silicon or germanium technology or something like that. So I wouldn't have expected anything like that. I would have expected it to ramp up, you know, similar to what we saw before. At least, you know, maybe a volt or something like that based on the current, even, you know, a volt and a half, something like that. So that seems grossly out, but that could be because we're in circuit. We got one! Yes! Check it out. I probed pins 1 and 8 here. Here we go. Pins 1 and 8 of our inverter chip, and this is what you'd expect. This is a diode characteristic curve. Starts ramping up at a silicon diode characteristic curve. Starts ramping up about 0.6, exactly what the modern 1N4148 does, and at 50 milliamps, okay, we've got 1.1 volts drop, okay, so it's not a particularly high current diode at all, but that, bingo, it doesn't, maybe that is not connected to anything else in circuit, and we have ourselves a classic diode characteristic curve there. This chip still works. The semiconductor inside still works after all these years, straight from the 1960s. Beauty. What a Bobby Dazzler. This actually works. I can't believe it. So if we probe these again, it really is rather a bit tricky. I've got to sort of hold it with two hands like this and get the tongue at the right angle. Here we go. Tongue's at the right angle. And there we go. It is really quite tricky to get the contacts right on this thing. And yeah, look, you end up with like little wiggles in here like this if you don't get the contacts right. I'll print screen that and show you that one up close. And yeah, you get these awful little wiggles in there and stuff like that, you know, just through the you know, at the microscopic level of how you're actually probing these things gives you all sorts of weird and wonderful stuff. So you really got to use these really sharp probes, and also the ones with the pressure, with the spring-loaded ones as well, really quite help to, you know, try and pierce these things and keep an even pressure on that joint. So we can get it though. Fantastic. Well, this is a bit of a wimpy test, I think. We're only talking like 0 to 50 milliamps I'm testing this thing at. This is capable of a couple of amps at hundreds of volts. So let's ramp it up. So I'll ramp up my current limit. Here we go. Start from 0 amps. It's going to go up to 1 amp in. I've got like 100 steps in there, which is more than adequate to get the resolution on our graph, and a compliance voltage where it'll cut out at 10 volts. So let's give that a whirl. If we break it, we break it. Wow, look at that. That's a rugged little bastard, isn't it? Look, 1 amp, and we ramped it all the way up. Didn't blow at it. Well, presumably I haven't run it a second time. Those wiggles, as I said, are just little contact issues in there. We can't actually get it to do straight if we probe it well enough. But yeah, it basically still ramps up at that 0.6 volts, and then basically completely linear region right up here. Yeah, sure, we're getting like a 4.2 or 4.3 volt drop at an amp, but geez, you can't blame it. Nice. Let's ramp it all the way up. And I've gone for these beefier ProbeMaster probes for the higher currents. Once again, these are incredibly sharp tips, but they got no spring point on there, and they got nice finger grips on them, so I can really get in there and probe the pins like that solid. And this is what we get. And I had a compliance voltage of 5 volts here, so that's why it's crapped out there. But you can see how we had that linear ramp before, almost linear. It sort of starts to tape off a little bit as it approaches 1 amp there at 4 volts. And then it really starts to tail off, so we're really losing the non-linearity of the diode here. So really its operational range sort of seems to be like, you know, not even an amp, maybe sort of, you know, to be conservative, I'd say probably, you know, like a half amp rated diode or something like that. So as you'd expect, these things are designed for low current, you know, operation, because these are a digital computer. They're, you know, working in the order, as we saw on the schematic before, order of like, you know, several K to sort of tens of K pull-up resistors, stuff like that. So we're really just pushing this thing silly to see where we break it at the moment. It's not really a half amp or 1 amp operational diode, that's for sure. And there we go. Look at this. This is interesting. I changed the compliance voltage to 10 volts here. So I'm ramping from 0 to 1.5 amps here. I stopped at 1.5 amps. And look at this. Here's what we saw before with the sort of the 1 amp curve like that. And it starts to taper off as we saw. But then it starts to taper back up. Look at that. So there's some weird characteristic going on there. Now it's actually better off if I don't kill this thing. So what I'm going to do is I'm going to try and slide out this inverter chip here. It's the only one that I've got, so I've only got one shot at this. So basically I've got to remove several of these other pins around here, just so that I can sort of, can I get the iron in there, and yep, no problem whatsoever. So I can get rid of these. And that'll help me slide it out, of course, otherwise they will be in the way. This is not elegant by any stretch, and not recommended for repairing Apollo era boards. This is not an approved repair technique, so please no flame emails or comments. And there you go, there's one of those little clips designed to, like, welded, the bottom part of that was welded onto the board in some way, shape or form, and then yeah, they were just designed to clip into those modules, so that has seen better days. And here we go. What I want to do is I'm going to try and sort of lever it under this end and slide it out this direction. And the good thing is, what I was probing before, I was actually probing pins 1 and 8 here. Yes, they're not labelled in the usual way, but that's what they're, well, the modern way we're used to here, but pins number 1 and 8, so I really only have to slide it out a little bit, and then it's not making contact with there. Because the idea here is just to slide the chip out, so then we can possibly get access to the top of those pins in there without having it in circuit. I just want to re-verify that diode in there, that PN junction, just absolutely sure it's not in circuit. And here we go, it's time to brutalize it. Yes, this is awful. I'm getting my screwdriver in here, but I just want to see if it budges. It does budge, look. It does budge. I'm probably going to, I might destroy this chip here, but if I can slide this puppy out, yeah, there we go. Slide in. Slide in, maybe if I come in this angle. And ta-da, we're out. We're out. There we go. That's good enough. And I should be able to now get in there and probe if there's any of those pads left. I don't know. I don't know. Presumably they were just like press fit on there, but who knows? They may have corroded off. So hopefully, well, we'll see if we can get in there and access. You can see this top one has some metal left on it by the looks of it. I'm not entirely sure about the bottom one. It could just be more looks than anything. Oh well, we'll see if we can still probe it. If we can't, oh well. And yes, bingo, we got it. Look at that. It is basically exactly the same as what we got before, ramping up at about 0.7 volts or thereabouts, and sort of half an amp. We're looking at like 2.2 volts or something, and then ramping up to an amp. I didn't take it any higher than that at this stage, and you can see it tapers off there. So that one was pretty much, if it was in circuit, there really wasn't any major effect there on it. So that is the characteristic curve of a 1960s era Apollo chip, one of the very first semiconductor chips ever made. Fantastic. And yet, there we go, I ramp it up to 1.5 again. We get exactly the same as what we got before, that little contact wiggle in there. And that's it. So that's the characteristic curve going up to 1.5 amps. Grossly overloaded to what this thing was designed to do. That's a bit mean. And there is the chip actually fully removed there, and we can see the bottom of that. Here we go. Nobody's seen the bottom of that chip since it was installed back in the 1960s, and it's got some sort of paint or some sort of epoxy type base on it. And I tried to measure some of the other internal resistors in there to see if we could get a linear response out of them, and I couldn't get anything. It's like there's no internal contact in there at all. I tried 3 different resistors and couldn't get any of them. It was just flatlined. I couldn't get the linear slope that we expect out of a resistor. But I've actually done this previously, probing around in circuit, and I did actually find one on the board. I just can't find one in this inverter, so let me show you the one I found previously. So according to my notes here, that pin there and that pin there and that one over there should be, to both of those should be 4K4 resistors. And here we go. This is really easy to probe. The back here, it just goes straight down the via holes. Nice. And we'll measure that. Bingo! There's our straight line characteristic curve of a resistor. That's from 0 to 10 volts. Completely linear. Exactly what you'd expect from a resistor. I can take that to higher voltage. Why not? I feel ashamed to do this to a classic Apollo era board, but here we go, 0 to 100 volts on this poor little resistor. Let's go. Ah, out of range. Wah. Fail. Unfortunately this bloody SMU has got an interlock circuit on it, so you can't go over 42 volts on the output unless you connect some digital interlock thing. And I read the manual, it didn't give me pinouts for the connector on the back where I have to connect the interlock and all that sort of garbage. Well, anyway, we went from 0 to 40 volts and it's completely linear right up to 40. Awesome. And well, to get back to where this thing is realistically used, I mean, 0 to 20 milliamps, for example. Look, I mean, classic diode characteristic curve, perfectly fully functional diode even today, even at 20, 20 odd milliamps, about 0.9 volt drop, down at 5 milliamps here, only about, 0.77 volts drop or something like that. Perfectly adequate diode for then and now. Really, yeah, it's not crash hot, but for just the signal operations that they wanted this for, DTL type stuff, diode transistor logic computer stuff. And if you're curious to know the leakage there, no, basically bugger all. Of course, you just put the diode in reverse from 0 to 10 volts there. It's, basically like in the order of 0.1 microamps. So pretty much on par with a 1N4148. So there you have it. That's a 1960s era Apollo launch vehicle digital computer logic board. Fantastic. And the diodes and resistors, the deposited resistors and everything in here still work and they're still functional. Fantastic. So you've got to wonder, if you kept these things in pristine condition, those Saturn rockets that are still, there's a few of these still sitting inside the Saturn rockets, I believe, that are inside the museums that you can go and see the remaining ones that they actually built. They would probably, good chance that the majority of them would still work today. Yeah, you'd probably have a few issues. You might have to swap a few boards or something, but hey, that's pretty awesome for 1960s era technology. I love it. And that's a perfectly usable diode characteristic curve. Yeah, sorry I don't have the time or anything to measure the transistor inside this thing. It was hard enough getting the damn diode, but the deposited resistors in here, perfectly fine and linear. Diodes, fantastic. So it still works. My thumbs up to, two thumbs up, to the Apollo era designers who pioneered all this stuff we take for granted these days. And this is one of the world's first, earliest, fully integrated digital, IC based computer. I mean, amazing. They've only got a couple of diodes, couple of transistors per chip. Now we're talking, hundreds of millions of transistors per chip. Is just in our phone and in our watch. It's just crazy stuff. But anyway, thank you very much, Fran, for loaning me this fantastic vintage board. And the idea was to pass this thing around to other people to do other stuff with. So I think, I've done my little part. I've used my source measure unit. Sadly, this has to go back to Agilent in a day or two. And yeah, so we confirmed that this thing still works or is still viable today. Fantastic. So if you want this thing, I'll pass it on to you. And if you've got an idea of some videos you want to do, of course, it has to be made public, all the info and videos of it. But if you want it, please contact me. Thanks, Fran, and I'll link to Fran's videos and her blog page down below as well. And she's got a new podcast thing, a new video show happening with Bill Hurd, I believe. So check that one out too. It'll be linked in down below. Catch you next time.